All of you, welcome to the session today. We are going to talk about Bose-Einstein distribution law. So, in the previous class, we have seen Maxwell-Boltzmann distribution law. Bose-Einstein distribution law. So, we made few assumptions. So, in this distribution law, already have seen. So, now the first one is the particles are indistinguishable. The particles are indistinguishable from each other so that there is no distinction between the different ways in which Ni particles can be chosen. Okay, see that the first condition is the particles are indistinguishable from each other so that there is no distinction between the different ways in which Ni particles can be chosen. Now the second point is each energy state that is ith quantum state may contain 0, 1, 2 up to Ni identical particles. Okay, so this is what second condition. Now the third one is the total energy of system. We know this one very well. The total energy of the system is equal to the sum of energies of all the particles distributed. The total energy of the system is equal to the sum of energies of all the particles distributed in different quantum groups. So therefore what we can say that the total energy of system remains constant, and also the total number of particles in the system also constant. Okay, now so here similarly, just like Maxwell-Boltzmann law, here we can take a box that is divided into GI subshells. Okay, so we are taking a box or cell, it is divided into subshells. So that means GI subshells are there. How many subshells are there? GI subshells are there, where in which Ni particles are distributed. Ni particles are distributed among these cells. Now the GI subshells here, GI subshells are constituted by G minus 1 partitions, right? Partitions. See there, for example, 1, 2, 3, 4, 5, 6, 7, 8. 8 cells are there. How many cells are there here? 8 cells are there. See, let us see Gi minus 1 partitions are there or not. Let us count it. 1, 2, 3, 4, 5, 6, 7. So that means how many partitions we have where Gi equal to 8 cells. And number of partitions can be what? How much? Gi minus 1. That means what here? 8 minus 1 equal to 7. See there, 1, 2, 3, 4, 5, 6, 7, 8 cells are there, and the number of partitions 1, 2, 3, 4, 5, 6, 7. 7 partitions are there. So therefore, the number of permutations, here we can write the number of permutations, the number of permutations is the number of permutations can be the formula is Ni plus Gi minus 1 factorial. The number of permutations can be Ni plus Gi minus 1 factorial. Okay, what is Ni? We know that Ni nothing but the number of particles distributed in Gi cells, where Gi minus 1 means the number of partitions. Okay, now the total number of ways the total number of ways in which Ni particles may be distributed in GI cells or see that the total number of ways in which Ni particles may be distributed in GI cells can be like this: Gi into where the number of permutations Ni plus Gi minus 1, here we have to write factorial. So let us assume this is what equation number 1. Okay, now so the particles are distinguishable. The permutations of particles among themselves will not give rise to indistinguishable arrangements, since there are how many number of particles are there? Ni number of particles are there, right? So Ni factorial. So such permutations, equation 1 must be divided by Ni factorial. See, let us divide this equation number 1 by Ni factorial. We'll get there Gi and Ni plus Gi minus 1 factorial by Ni factorial. So now, since the energy states also quantized, since the energy states are also quantized, equation number 1 must also be divided by Gi factorial. So let us divide above equation with the Gi factorial. What we get there? We'll get there Gi Ni plus Gi minus 1 factorial by Ni factorial into Gi factorial. Alright, so from this equation we'll get this can also be written as Gi and Ni plus Gi minus 1 factorial. So by here we'll write Ni factorial remains same. This can be written as Gi minus 1 factorial into Gi. This can be written as Gi minus 1 factorial into Gi, where Gi cancel. So finally we'll get there here is the resultant 1 Ni plus Gi minus 1 factorial by we have Ni factorial into Gi minus 1 factorial. So this is what equation number 2, let us assume. Now the total number of ways in which N1 particles can assign to the level with energy E1. See there the total number of ways in which n1 particles can be assigned to the level with energy E1 here E1, and similarly N2 particles can be assigned to the level with energy E2 and so on is given by the product of such expressions as given below, where we can write here the function g equal to, so from equation 2 we'll write that n1 plus g1 minus 1 factorial by, here we'll write n1 factorial and g1 minus 1 factorial. Now again we'll write there n into n2 plus g2 minus 1 factorial by n2 factorial and g2 minus 1 factorial. Similarly, finally we'll get there here ni plus gi minus 1 factorial by ni factorial into gi minus 1 factorial. All right, so now this can also be written as where g equal to pi, and we'll write ni plus gi minus 1 factorial by, so ni factorial into gi minus 1 factorial. So this is what equation number 3. Okay, equation number 3. Let us assume now what I'm going to do here is, so since where ni means the number of particles, where gi means the number of shells, so they are large numbers, so let us neglect minus 1 in this equation. Then finally what we get there, where g equal to pi, and we are neglecting minus 1 plus ni gi factorial by, where we'll get there ni factorial into gi factorial. All right, so let us assume this is equation number 4. Now let us apply log on both sides. So for what we get there finally, otherwise ln, if we apply ln on both sides, we'll get ln, the natural logarithm ln g equal to, it will become summation, and well, we'll write ln ni plus gi factorial and minus ln ni factorial minus ln gi factorial. Okay, now so we know that Stirling's approximation, we know that, let us apply Stirling's approximation. So if we apply, we know that that is what here Stirling approximation means. Ln x factorial can be written as x ln x minus x. Okay, so what we get there finally, if we apply this formula to above thing, then we'll get there ln capital G equal to summation. Here this can be what we get there, ni plus gi and ln ni plus gi and minus ni plus gi. Okay, next this can also be written as where ni and ln ni and minus into minus plus ni, and similarly here we have the function minus gi ln gi and minus into minus plus gi. All right, we'll get this one here. We know that the term, these things and this one cancel, and finally what we get there, finally we'll get there so here ln capital G equal to, so we'll get there summation. Here we have the term ni plus gi and ln ni plus gi and minus ni ln ni minus gi ln gi. Okay, so we have this function. Okay, phone chesturu baby pillalu. So now we got ln capital G equal to summation ni plus gi ln ni plus gi minus ni ln ni minus gi ln gi. Okay, now here So what I'm going to do here is I'm taking partial differentiation on both sides. We know that this is the maximum value where Malay. So now let us take partial differentiation on both sides. Then we'll get this is the maximum value, and then change in maximum value will be 0. So we know that dou log e, where I'm instead of taking ln and I'm taking log e, and the g maximum equal to 0, right? So by doing this, then what we get there here, summation I, and here I'm taking there where gi is constant and we have only dou ni, and this can be written as log e ni plus gi, log e plus ni plus gi plus here take this is what xy, what I'm doing, I'm taking differentiation of xy. So where dou ni and this remains same, and plus this remains same now, ni plus gi remains same, and the differentiation of log value will be what there, 1 by ni plus gi, and the differentiation of this function can be dou ni. Okay, so minus this can be dou ni, and here it is dou ni ln ni, which remains same. So this can be written log ni, and the minus again we'll get there, minus ni into 1 by ni into dou ni, and this function, differentiation of this function will be 0. And finally that equals 0, where ni and these two things are cancel. And finally what we get there, and this function and this function also cancel each other. Then finally we have the term here is the summation I, here have to take log e ni plus gi minus log e ni, and close the bracket, and we have the term dou ni equal to 0. Okay, so let us assume this is what equation number 5. Now we know that where summation I ni, that is what total number of particles is constant. So now if you take change there, summation I dou ni equal to 0, right? Now similarly assume this is what equation number 6, and similarly summation I, we know that the total energy of the system remains constant. This can be ei ni is constant, and if you take change on both sides, change in total energy will be 0, right? So summation I ei dou ni equal to 0. Assume this is what equation number 7. All right, now what I am doing, just like what we did in Maxwell-Boltzmann statistics, here also we have to do, take equation number 5 plus, and what I am taking there, minus alpha into equation number 6, and here I am taking minus beta into equation number 7. Now see what we get there. We know that equation number 5, what is that equation number 5? This one is equation number 5. Okay, now let us take summation I, and where it is log e and ni plus gi. Okay, so minus log e ni, I am taking this one here. What we get there, if you take these two things, what we get there here, we'll get there minus, here we have alpha and minus beta ei, and take dou ni common, then what we get there, close the bracket, and we'll get there dou ni equal to 0. All right, now so finally what we get there, see what I'm doing, I'm writing this one as summation I under dou ni, and finally we'll write this one as like this. See there, log e ni plus gi by ni, we know very well this can be, these two steps can be written as like this, log e ni plus gi by ni. and minus alpha minus beta ei, okay, equal to 0. All right, so now finally what we get there, here I'm writing this one as ni plus gi by ni. If we remove the log function here, we'll get there here e to the power of minus alpha plus beta ei. Okay, so we'll get exponential term, and this can also be written as, here this equation can be written as this, that can be written as 1 plus gi by ni, so that equal to e to the power of alpha plus beta ei, and gi by ni equal to e to the power of alpha plus beta ei and minus 1, and finally ni equal to gi by e to the power of alpha plus beta ei and minus 1. All right, so this is our required equation. So according to BOSE-Einstein, the distribution function can be ni equal to gi by e to the power of alpha plus beta ei minus 1. So this is our required equation, where beta is equal to 1 by kt. Okay, so this is our required equation. This can also be written as ni equal to gi by exponential of alpha plus beta ei and a minus 1. Okay, so this is known as BOSE-Einstein distribution law. This represents the most probable distribution of the particle among various energy levels for a system obeying BOSE-Einstein statistics. If you take the plot versus the number of particles ni by gi and energy function ei, so we'll get this curve like this, where so this one represents low temperature region, and where this curve represents high temperature region.